Welcome to my video course on AI application for railway signaling. Today, we're diving straight into the really incredible ways artificial intelligence is completely transforming how trains navigate, how infrastructure is maintained, and how entire railway networks operate.
Here is a quick look at our agenda. We'll be covering AI and railway signaling, supervised learning for recognition, unsupervised learning for anomalies, reinforcement learning in traffic, and we'll wrap up with the cognitive railway future.
Let's get right into Section 1, AI in railway signaling, the foundation. So, as a quick baseline, machine learning is a crucial branch of AI that identifies patterns and makes decisions without being explicitly programmed for every single specific task. Instead of writing millions of lines of complex rules, we just feed the system data and it literally learns from experience. It's pretty amazing. And there are three primary branches of machine learning powering our modern railways: supervised, unsupervised, and reinforcement learning. Each one tackles a fundamentally different type of problem, and together, well, they form the absolute backbone of next-generation rail networks. Moving on to Section 2, supervised learning for recognition, training with knowns. In this approach, we feed the system thousands upon thousands of labeled photos. We are effectively teaching the software what a train or a signal actually looks like. It's like giving the computer an answer key. We show it a picture, tell it exactly what's in that picture, and we repeat that until it can reliably recognize those objects on its own. Just look at how these bounding boxes are drawn around the rails here. By localizing the tracks in our training data, the model can calculate pixel distances and accurately determine a train's exact position. We're essentially teaching the AI to pinpoint tracks in real time, which helps the train understand exactly where it is, and more importantly, what's right in front of it. Now, by using ultra-fast object detection systems, the model can recognize main tracks in over 95% of frames. And when you think about how fast a high-speed train actually moves, processing visual data in fractions of a millisecond isn't just a nice-to-have, it's absolutely vital for maximum safety.
But we do have to account for edge cases in supervised training. For instance, a model might completely fail to localize tracks when they're obscured by heavy snow or hidden away in really dark tunnels. Supervised learning is fantastic for sure, but its performance is tightly tethered to the variety and quality of the environments it was originally trained on.
Which brings us to Section 3, unsupervised learning for anomalies, discovering the unknown.
This poses a really critical challenge for infrastructure maintenance. How do we detect a completely new type of equipment failure before it causes a major disruption? If we've never seen a specific part break in a certain way, we obviously can't give the AI labeled photos of it. So how do we spot the problem?
That's where unsupervised learning comes in. By analyzing continuous, raw, unlabeled data streams, the system establishes a baseline of quote-unquote normal behavior, allowing it to autonomously discover hidden structures and instantly spot anomalies. The AI simply watches the equipment run day in and day out. Once it learns what a healthy system looks and sounds like, any weird deviation from that norm immediately throws a red flag.
This is a real game changer because it allows us to extract risk vectors and detect unusual equipment behavior in track circuits or switch machines long before a critical failure actually hits. By processing time series data from SCADA systems or even analyzing subtle changes in vibrations and sounds, the AI can predict a breakdown proactively. It's way better than just reacting to a broken rail after the fact. Let's shift gears to Section 4, reinforcement learning in traffic, dynamic decision-making.
In this learning loop, an agent learns to act by interacting directly with its environment, receiving rewards for correct actions. You can kind of think of it like a video game. Whether it's safely navigating an autonomous UAV drone or robot for track patrolling, or optimizing a complex traffic route, the AI tries out different strategies. Safe, on-time arrivals, win points. Delays, lose points. Over time, it figures out the absolute best strategies to maximize its score. So instead of just blindly reacting to traffic, this model learns local transition functions to proactively minimize delays and resolve path conflicts across the entire transit corridor. It's incredibly relevant for situations where decisions constantly change the state of the network. It literally looks at the whole board, anticipating where bottlenecks are going to happen before they even form, and smoothly adjusts speeds and signals to keep everything flowing safely.
And finally, Section 5, the cognitive railway future, sense, decide, act. By fusing supervised, unsupervised, and reinforcement learning, AI doesn't replace human domain expertise. No, It amplifies it by creating a continuous sense, decide, act loop. The cameras sense the tracks, the anomaly detection monitors the health of the equipment, and the reinforcement learning decides the absolute best traffic flow. It's this brilliant, unified system that acts as a true partner to railway operators.
As machine learning pushes railway optimization to its absolute limits, we have to ask ourselves, what new autonomous frontiers will cognitive railways conquer next? The tracks are laid, and the AI is always learning. Thanks, we can see you next video.